Right. Welcome, everyone. Sorry about the wait for a few minutes. Welcome to our first session for Thursday. We have a really exciting talk lined up. It's to do with how not to let your model and data drift away silently. And I think it's extremely relevant because machine learning is not a one-time thing, right? You don't just train something, put it in production, and forget about it. We almost have to keep an eye on it, and especially I know from personal experience, and I work in retail and supply chain. So when COVID happened, it kind of threw a lot of things, out for us, and having the need to monitor things and make sure that the data and the model don't drift away, and you're able to have those tools and capabilities to make sure that things are going well is extremely important. So I'm very happy to have Chengyin Yang today to talk to us about it. Chengyin is a data science consultant at Databricks, where she leads a cross-functional customer projects and implements scalable end-to-end machine learning solutions. She delivers machine learning workshops with topics ranging from deep learning, natural language processing, and machine learning in production. She received her master's in computer science from the University of Massachusetts Amherst and completed her BA in environmental studies and statistics at Mount Holyoke College in Massachusetts as well. So without further ado, Chengyin, please take it away. I'm really looking forward to this talk.
Yeah, hi everyone, welcome to this talk. My name is Chengyin Eng. So by the end of this talk, you'll be anchored with a suite of useful tools and also open source package options to test both your model and data validity in production. So I'll just skip over this introduction slide since Kanchana did such a great job of covering all the grounds here. So for this talk, we're going to discuss the ML lifecycle and why we care about drifts and tests, and not only what we should monitor, but how we should monitor. And lastly, I will be summarizing all of this in a workflow that you can implement for your own use case. And I will also share with you a code example that I have that I've implemented as well. So there are a lot of reasons why machine learning projects fail, and here we just focus on the production phase. And the top reasons why ML models fail to perform in a long-term production setting is that most data scientists neglect the importance of maintaining machine learning models post-deployment. So a lot of us think that our jobs are complete once we're able to ship a model to production. Hence, we actually overlook the importance of testing and also our models and also data in production to ensure that the model quality is consistent across time. So perhaps it's not that surprising because ML Ops, which is the set of best practices of machine learning operationalization, is still a really new field. And so oftentimes there's a lot of confusion around where to apply the statistical test, and in particular, what test to use. So this is the area my talk hopes to shed light on. The first is, what are the statistical tests that we should use when monitoring models in production? There are a lot of proprietary softwares that partially address this question, but today I want to introduce you some open source package options that you can use for your own project. And the second part here is, what tools can you use to coordinate the monitoring of data and models? So in particular, later in the code example that we're providing, I focus on testing tabular data in a batch scenario. But just note that the statistical tests are relevant across the streaming and those real-time deployment settings as well. So you can borrow the same overarching framework and to adapt that to the other types of data, such as images and also text. So in this talk, I will not be covering any strategies of model deployment. I will not be covering any unit tests or integration tests for your code. And because testing and monitoring is so unique to each use case and domain, this talk is by no means providing a prescriptive manual of when you should update your model. And instead, I'll be covering how to detect those feature changes and model stillness. So before we dive into the nitty-gritty about the tests, I'm going to talk a little bit about the ML lifecycle and why we should monitor it. Our ML system typically starts with defining a business problem, translate that into a data problem, defining appropriate success criteria, and then following that, we will collect the data that we need, do additional data processing or feature engineering, train a model, evaluate a model, and if we are satisfied with it, then we deploy it. But for a robust machine learning system, we should actually set up model monitoring and use the information from that model monitoring section and to inform the feedback loop. So why is model monitoring important? Model deployment is really not the end. The quality of our model greatly depends on the quality of our data. And the data distributions and feature types can change over time due to multiple factors, such as upstream data errors. Maybe you had a temperature column that was previously in Fahrenheit, but now it's in Celsius. There's market change, there's human behavior change as well, and all of this can lead to potential model performance degradation. So the question here is not really about if a model will degrade, and it's more of a question of when a model will degrade, and if we can identify this before and when it happens. And when we identify the drifts that happen, then we should also be aware of what actions we can take as a result. So before we look at the statistical tests that we should have in place for the production models, we should first understand what are the types of drifts that can occur in production. So here I've largely categorized the type of drifts into two categories. First is data drift, where your input features, your label, or your model predictions can drift. The second part is concept drift, which is also commonly known as market drift, which is where your external factors can cause the label to evolve. So what this means is that your distributions currently can be different from the distributions that you were having in production setting. So this is what it looks like. On the left, we have a categorical feature. We typically use a contingency table with expected count and observed count to look at if the distributions of the counts are different. And on the right, we have histogram that shows continuous feature drifts. So you can see that the gray histogram shape has shifted slightly so that we can see there's an increase in mean and also variance as well. For concept drift, it can manifest in many different manners. The first is sudden, which is due to unforeseen circumstances. The second is gradual, which means that there's often a transition phase where you have a mixture of two types of observations with varying proportion. So it might not affect all the cases at once, and initially might affect some cases, but not the others. And it will gradually affect more and more cases until it becomes visible across the board. And the third is incremental, which means that there is actually a lower ratio of change. So you can see in this visualization that the difference between the blue dots and the red dots are not so significant. The last one that we see over here is recurring, which means that a previous iteration may reappear, and it may happen only once or periodically. So now that we have identified the type of drifts, let's look at the actions that we can take. So I want you to look at this table from left to right. So let's first take a look at the feature drift. So when a feature drift happens, then we should either retrain using new data, or we can investigate how the feature is generated. So on to the second type of drift here, which is label drift. Similarly, we can also retrain using new data, and we should also investigate how we generate that particular label. The third type of drift over here is prediction drift. So here, we typically have to investigate how the model is trained, if there's something wrong during the model training process, and we should also assess the business impact. The last one, concept drift, which is can be the most dramatic shift right here, which means that we sometimes can retrain or just tune using new data, and that will work. Or other times might actually have to investigate other alternative solutions or do additional feature engineering. Okay, so now let's look at what we should monitor. There are four aspects altogether. First is the summary statistics of features and target. We should also monitor the model performance and metrics as well. And for instance, we should only replace the existing model in production if the candidate model performs equally good or better. And the last one over here is business metrics, just so that we can see if the change in business metrics will affect the relevancy and also impact of the model. So now let's move on to the specific monitoring tests on data. And we should first identify which features are numerical or categorical. So for numerical features, we can compute things like median or mean, minimum, maximum, percentage of missing values. In terms of the actual statistical tests, for means, we can use the two-sample Kolmogorov-Smirnov KS test with Bonferroni correction, or the Mann-Whitney test. And for variance, we can use the Levin test. So before I cover the categorical tests, I will first go through the basic concepts of what we are seeing here on the slide. So let's examine the KS test with Bonferroni correction first. KS test is particularly useful when we want to compare two continuous distributions. So the null hypothesis here is that distributions X and Y come from the same population. So if distributions X and Y are different enough at a P level of certain alpha value, so usually it's 0.05, then we reject the null hypothesis and conclude that distributions X and Y do not come from the same population. So sometimes we encounter type 1 error, which is when we reject a null hypothesis when it is actually true. And especially as we repeat this KS test for a number of features, say n, then the rate of false positives actually increases. So this is why we need to apply the Bonferroni correction to adjust the alpha level by the total number of feature comparisons to reduce the family-wise error rate. So just note that this framework of hypothesis testing over here will be repeating for other statistical tests we'll be talking about as well. So let's look at Levin test. Levin test specifically compares variances between two continuous distributions. It also tests a null hypothesis that both distributions come from populations with equal variances. So if the Levin statistic has a p-value that's lower than a preset alpha, like say 0.05 again, then reject the null hypothesis and conclude that both distributions have different variances. Now let's pivot to the test for categorical features. So similar to numerical features, we can compute the percentage of missing values, and other summary statistics that we can include are mode and also your number of unique levels. In terms of a statistical test, we can leverage the one-way chi-square test. The one-way chi-square test compares the expected count and observed count of a categorical variable. The null hypothesis is the observed distribution, which is the incoming data, is equal to the expected distribution, which is the data in production. So similar to before, if the chi-square statistic has a p-value that's lower than alpha level, then we reject the null hypothesis. So we have been talking a lot about what tests we should use for monitoring. In the next slide, we'll be discussing the monitoring tests that we can implement for models. There are a few aspects about a model one might care about. First up is the relationship between the target and features. So we may want to investigate a correlation between the inputs and the numerical targets, especially when we are only using a select few features that we previously found to be important. So we still want to make sure that they are still relevant and important to predict the target. The next up is model performance. So I bet this is the most obvious piece to many of you. For regression models, we can check for MSE, R-square, and for classification models, we can use ROC, confusion matrix, and F1 score, etc. And I also invite you to assess a model in more granular terms as well, especially by investigating performances on just specific data slices. So for instance, we can assess the performance on data, say, by month or by product type, or even by certain PI attributes that you care about to investigate fairness and bias as well. And lastly, we can also be cognizant of the time taken to train a model. So if a model is taking, say, triple the time to train compared to before, when nothing has changed, then this could be a telltale sign that something is really fishy. So how should we monitor? I'm going to show you a workflow that I've implemented myself, and you'll also be seeing the same workflow in the code that I'll be sharing later on too. So you can see that we start with month 0, which is when we train a model on data, which is when this is the first time we're training the data, so there's no historical data to compare against. So assuming that we are doing our due diligence of training a model, tuning a model, and then we eventually deploy that in production. So now month 1 data actually arrives, which means that there is new data. So at this stage, we can check for nulls, summary statistics, use KS tests and Levin tests and chi-square tests to detect if any of the differences that we see in the summary statistics are statistically significant. So if this test passes, then we can proceed to train a new model. But if any of these tests fail, or if there are statistical differences are not significant, but you still care about the differences that we see in summary statistics, then you might want to address the drifts or the concerns before we train a new model. So now that we have trained a new model, before we transition that to production, then we should actually ask if the new candidate model is better. So this is one of the most basic tests that we can check is whether our new model is performing better. And if it is, then we can replace the existing model in production. And if not, then we should not replace the existing model, and we should go back to the sketching board and do more model training or tuning or investigate other approaches. And then you can see that I've drawn this orange box around the month 1 onward. So you can see this framework repeating for the future months as well. So let's look at the tools that I might use for each of those tests right here. So you can see that for statistical tests, I can use SciPy, stats models, Seaborn for visualization. So these libraries do cover quite a lot of grounds, but they are still not as comprehensive yet, which is why we still need to have some custom implementation to make sure that we actually are addressing all the concerns that we have about the data. And the second part here is to check if the model performance is better. So this, thankfully, the test is not too hard to write. You are just comparing two numbers. And you may want to set a threshold as well. You'd say if R squared improves by 0.05, then you would transition. If anything less than that, then you would not. And overall, this entire workflow can be tracked and also versioned. So for models, we can look at tools such as MLflow. And for data, we can actually look at Delta, which is an open source data storage format. So let's briefly discuss MLflow and also Delta. So MLflow is an open source tool that helps with ML ops. There are 4 components altogether: tracking, project, models, and model registry. So in my workflow, I particularly use tracking, models, and model registry. So tracking is particularly useful when you want to record an experiment, which means a single executional run that you have to train a particular model. And you can track the code, you can track the metrics, you can track the hyperparameters, you can track artifacts as well. So that is really handy. And then MLflow models actually help us to package the models in such a way that it can be easily deployed to different environments because it standardizes the deployment options. And it's a very general model format. And lastly, model registry is a centralized and also collaborative UI that you can manage the model lifecycle. So here I'll be showing you the experiment UI of MLflow. I don't think I have too much time to go into the notebook example later on, so I will just be highlighting the notebook workflow, and then you can take the code to view it at your own time. So you can see there is an experiment UI over here where you can see the experiment ID, artifact location, and all the different runs, and also the associated parameters and metrics. And this is what the model registry looks like, where you can see I have different versions of models over here, and they're in different stages. So let's talk about Delta. Delta is an open source data storage format. It actually is really just a fancy term for to indicate that it's a combination of Parquet files with transaction logs. So you can see here in my first screenshot right here that says Parquet and also a bunch of JSON files. So Parquet is where the data actually lives. So JSON files are the files that keep track of the changes. So it means that you can now easily version the data and also keeping track of the updates. So which is why you can see in the second screenshot at the bottom right here, where you can actually read older versions of data by specifying a timestamp or a version number. And if I were to get curious about table history, I can sort of just hop onto the time capsule right here and then just investigate the history version numbers over here. And then also, if I scroll over all to the right, then I can see the different operation parameters or the updates that have been made to this particular table. So without further ado, I will pivot to the notebook right here. So you can also download the notebook from this bit.ly link, which hosts the GitHub page. And our host, Kanchana, today will also be posting a link to the chat as well. So this GitHub link will give you the access to my slide deck and also to the notebooks that I'll be demoing. So let me pivot to the notebooks and stop sharing my screen for a second, just so I can show the notebook window. Yeah, so I will just give you a second to copy the link over there. And so you can see here that I'm using a Databricks environment, but you don't have to, because as I said, all the tools I'm using here are open source. And when you download a notebook, you actually notice that it is a directory of different files. So right here, I have this main notebook where I am actually training and also deploying a model. And then this notebook will be sourcing the functions from monitoring utils and also training setup. So for this particular model that I'm training, I'm using the Airbnb in Hawaii dataset because I know all of us are dying to go on a vacation and can't wait to go to the beach and just chill. And so the model here will be a regression problem where we are using the features on Airbnb properties and to predict the price of a particular Airbnb. So as I mentioned before, this workflow really follows the diagram that I've showed before in the slide deck. So I'll just be glossing over all this. And also just note that I will be covering this notebook kind of fast, but don't worry, because I will be just highlighting the high points for all of the highlights for this notebook, and you also have the code to run in your leisure as well. So you can see that in month 0, I have I'm loading the data, and then I'm training the data, training on the data, and then eventually deploy the models. So notice that there will be a lot of helper functions that I've sourced from two of these notebooks over here. So let's take a brief look at them right now. So first of them is the training setup notebook, where let me scroll all the way back up first, is when I am using MLflow, I'm using Delta and also Seaborn to just help me keep track of the model and also data, and then I will be plotting some visualizations using Seaborn. So you can see that here I have a bunch of configuration variables over here where I am querying from the MLflow to get experiment ID so that I can always log the same runs or the different runs to the same experiment. And then I have Delta tables over here where I will be able to keep track of the data versions. And also just note that for the purpose of this demo, I've simulated two scenarios or 2 months of feature drifts and concept drifts. So we'll be using the monitoring utility functions to catch those drifts in, when we train a model or before we train a model. So you notice that we have a number of numerical columns over here and also categorical columns. When scenario 1, we are simulating feature drift over here when there is a review score rating system that's being changed from 0 to 5 to 0 to 100 scale. And scenario 2 is when we have peak vacation season, so all the price for Airbnbs have gone up. So you can refer down to further below where we are writing some wrapper function just around the existing MLflow functions to suit to our own needs. And then in the monitoring utility functions, here is where you can find all the statistical tests that I have implemented. So you can see there is checking nouns, checking differences in summary statistics, checking differences in variances, and also checking using statistical tests like KS test, and also Levin test as well for categorical variables. And then we can compare the model performance right here. And then here is the visualization. So let me just go over this notebook in real quick. So you can see that when a model arrives, we always apply the feature checks first before model training. And then you can see there is checking proportion of nouns. This tells us if it exists a certain threshold that we care about, checking for different summary statistics, and then also plot some box plot. So you can see that from this one right here, then we can notice that there is a difference between the incoming data and also the production data, where things went from 0 to 5 to 0 to 100. And then now that we have some information about the summary statistics changes, then we can use statistical tests to check if they are significant or not. So you can see here that the only significant changes here is in the review score rating column. And then same thing for the categorical features. And then assuming that now we have resolved the data issues, we can train it. And then before we deploy, then we actually want to check if the model performance is better than before. So this was like a really, really speed up version of what I have in the notebook over here. But just note that you can download this notebook from the GitHub, and you can take a look at the notebooks the tests I've implemented. So you'll be able to play with this at your own time and also implement or borrow some of what I have over here too for your own purpose. So I just want to wrap up with some conclusions over here. Model measurement and monitoring are crucial when you want to operationalize ML models. ML deployment is absolutely not the end. And because each domain is so unique, there's really no one-size-fits-all solution. So you should absolutely implement other tests that are relevant to your own business use case. And lastly, a robust ML system also means that you need to ensure reproducibility. So if there is an event failure, then you can enable rollbacks. And it's also critical for you to maintain a record of historical performance as well. Okay, and here are also some resources that I've linked here. So you can feel free to check them out in your own time. But I am ready to take on any questions and comments.
Perfect. It's great talk, Chengyin. And I love that you put up the code. I think sometimes it's like people are able to see a talk, but they're not able to connect the dots. Like, because when they walk away, they don't know what to do with the information. So I'm really happy that you posted the code and your slides. So we have one question to start with from Monica Gomez. So the question is, the workflow is very useful. Thanks for sharing. In production, in what part of the pipeline and how and where do we add this code? here you show a notebook, but in production, where does this code live? A notebook wrapped in a Docker container, and so on.
It should just live wherever your code lives. Your model training code lives. So here you can see that I'm using a notebook environment over here, but I can also do it in PyCharm, where it means that after I train a model, then I will be sourcing another Python script. Then I'll be running the test on the particular code that I want to test before I move forward. So it means that all of this, it really applies to think about it in terms of where you want to apply, and then thinking about if you have the code as step 1, and then step 2 is where you train, and then maybe the second Python script right here would just be a really simple, like source this, and then you can check off all of the errors or the warnings right there.
Perfect. Yeah. Thank you so much. There's another question. I guess this is more of a technical or a admin question, which is, where is the notebook located on your GitHub? I believe you said it's within the zip file, didn't you?
Yeah. Let me show real quick. So it's bit.ly mlops_2021 drifting away. So you can see here that I have the zip file over here, which is in HTML format, which means that you don't have to use Databricks to be able to build my code. And for those of you who are using Databricks, then you can run this, use this particular file, so the DBC file. So I've also included some README documentation right here, so you can also look at this documentation to look at where you would get the slides, the notebooks, and how to make the code work, such as like creating a directory to and like the directional structure that you need. But of course, you're also welcome to just change whatever that I have in the notebook to make it work to your own directory structure as well.
Okay, perfect. Thanks, Shane. Are they okay? Like just when I thought there was no question. Okay, Bhushan has a question. What is a good standard to put concept drift in check?
Can you repeat the question? What is a good standard?
The question is, I guess, what is good standard to put concept drift in check? I'm assuming he means how to, he or she means how to fix concept drift. Maybe that's the question.
Yeah, so I would say that, it's ideally you should be monitoring the models in production, which means that maybe you have pushed a model to production and you are actually continually generating metrics from your models. Like maybe then you will inspect it maybe weekly or even daily, depending on your particular use case. And then from there, if you find that there is a significant drift from, like say, predictions or even labels, then that's when you might want to, retrain a model or investigate additional solutions. So all this is to say that, is when you deploy a model, that it means that you should set up a system where a feedback loop is enabled. You are able to check the results and you're able to respond to the results before it gets too dire.
And just to add to that, when you're doing it in practice, you want to automate it, but not over automate it. Like you somehow want to be able to set some alerts so that you can still keep an eye on it. While you're automating, like Shane said, you can automate a lot of those pieces, but you may want to just still keep an eye on it to make sure that it kind of makes sense and you're not kind of overtraining or kind of over adjusting for something that doesn't have to be the case. Awesome. So Monica has another question which says, as a follow-up to my previous question, do you have to sample the outputs of your model in production, therefore have an additional database for these samples, and then perform the statistical tests on them?
Oh, that's a great question. So I would say that it depends on how big your data is. So I know that some people would like to sample, like maybe say 10,000 rows, whatever, to inspect the drift. Some, if your data is not that big, you might actually apply the whole test on your entire database itself. So in terms of saving things to a different database just to track results, I would say that is not entirely necessary, or I haven't found the need to to implement such a system. But typically, if a model is in production, then what it means is just that now that you have a maybe a prediction data frame saved somewhere, because you are going to be querying from that later on after all, so then you will be drawing the results from that database to run the test on.
Thanks, Shane. That's actually great. That's a great, an interesting question. Almost like a nuance that you don't, particularly catch. Bhushan has another question. Should validation data always evolve when generating metrics such as CTR and conversion? Are the metrics too generic?
Oh, this is a hard question because I think it depends really on the use cases, and And so I guess I would say that, for all the metrics that I've shown so far, they are really general. So none of them is very specific about Airbnb or predicting prices. So in addition to the statistical test, then you should absolutely have tests that address your particular, like your what CTR use case. So then that would be leaving up to the domain expertise also define it as well.
Yeah, exactly. And I think that validation data is almost so critical, because with COVID, I think it changed a lot of things for us, right? On how we decide what validation means. Matthew has a question which says, in your experience, how quickly do models drift away? Is there a lot of variation between types of models or types of data?
Honestly, for this, I would say that most of the time it's pretty boring. So you don't really see a lot of drifts unless there's something really subtle where, maybe there's just an upstream data ingestion. So usually, most of the time, it's not something critical. So, okay, it's an upstream data ingestion, and you just want to talk to a data engineer to find out what's wrong. But, obviously in the last year, we all have experienced a black swan event like COVID. So that definitely changes things. So it means that, sometimes oddly enough, if you were to keep track of what is going on in the world, like that's relevant to your use case, it might actually also inform you what might actually, what affects your models.
Yep, absolutely right. And Monica has another question that says, do you have any suggestions about doing this if you have to monitor thousands of models at the same time?
There's no easy way. Yes, that is a headache. And yeah, I would say that, it's, for me, I would think about how I can put the generalized test in like maybe one library, or I'm sorry, maybe not even one library, just like one script, and then you will just be applying the same script to the thousands of models that you have, and then you will have model-specific scripts that you would run on the specific models. So that's the easiest way for me to think about how to make the code more easily organized is by having a really generous script that can be applied to all. But yeah, there is really no easy way because there's thousands of models. Yeah.
Yeah. And are there any more questions? I have one, Chengyin. Just take a step back. We talked about maybe using statistical tests and p-values, right? And we know p-values are kind of it's a kind of a weird concept. Like we know 0.05 is kind of accepted, but maybe it may not be the best for our use case. Like what do we pick? Like how do we make it useful for us? Like do we tie it back to something like accuracy and see, or do we have to do some pre-work so that we can get to some number that makes sense for us? Like how would you go about it?
No, yeah, that's a great question, especially when many of you might have heard about, about the problem of p-value, and sometimes it's not even telling us something that's useful. So I would say that, first of all, just a principle of setting a p-value is that you never change your p-value post hoc. So we should always set like a number that we are confident in or comfortable with. 0.05 is really arbitrary. If you're more conservative, then you can set it at 0.01. So I would say that set a threshold early on. That's a good principle across the board. And don't let the results afterward change your opinion about the p-value that you've selected. And so on to the point about the question about what should we use then in addition to p-values, I would say that is anything that is specific to your use case. So if something that is, so say that we have seen two continuous distributions have drifted according to this KS test, then can I actually look at other, for instance, because all of this KSS is checking the feature by itself, meaning you are comparing one distribution against like its own distribution, like old distribution. So maybe something that you can do is, okay, what about the relationship between one feature versus another, so that you can have more confidence about, or if the correlation between these two features were, say 0.95, and now it is 0.5, then that will also tell you something about the features, even though you don't have the significance level to tell you whether it's statistically significant or not.
Chengyin. Are there any more questions from the audience? I feel like this topic is really close to my heart. It's something I suffer with a lot. So
yeah, I mean, honestly, it's still an area that I'm still learning. So maybe you, the audience member, will have something to teach me as well. And hopefully this will be a conversation starter for future talks at conferences like this.
Yeah, I agree. And it's not as you said, it's not a one size fits all, right? Like you almost want to figuring out what to monitor is a question on its own. Figuring out how frequently, because sometimes it can be too expensive to monitor. Sometimes if you don't monitor and find it ahead of time, it can screw up with, say, a forecast that can in turn affect an entire supply chain, right? So the impacts are also varying. So did the audience have any more comments on this? Like maybe from your personal experience, anything you'd like to bring up? Okay, we have one more question. Jean has a question which says, what is the time frame that you compare the correlations between features or labels?
I would say as humanly in timely as possible. So as you know, one of the, I think it was Monica that said, you have 1,000 models, then what is feasible for you to do? Because ideally, even though we can run this test, automate this test, but we still would need a human to inspect the test. So I would say that is up to you to define like when it's most feasible to you. But also, it means that you have to strike a balance between like what is possible for you and what is likely to have changed in your particular domain. Like if say that a restaurant recommendation like system, if you what you know about the market is that there will always be, like maybe 10 restaurants will spring up for every 3 months. Then it means that the minimum threshold that you should check your model will be every 3 months. So something like that. So it means that it always has to be balanced with your knowledge about the market or the use case, and then combine that with a statistical test that we can implement.
Yeah, of course. Yeah, it's data science is all. That's why they're calling it more art and science together, right? It's not really here's an answer, use it and run with it. So I wish it was like that. I maybe have one question to wrap up if nobody has questions. So checking, how does the model that you've chosen kind of affect this process? Like, for example, let's say you're retraining or you're kind of looking at, training a model, say, every week. And sometimes, like when you train something like a linear regression or something like that, typically one extra data point or a few extra data points don't affect it a lot. But if you take something like tree-based model, like GBM, then because of the stochasticity, even a few data points can kind of really change the predictions and kind of really mess things up, right? Like, so how do we balance that model choice versus the data drifting piece?
Yeah, that's a great question. And I would say that, I'm just going to show this diagram right here. I would say that the model choice here, we should absolutely know the pros and cons of the models before we even use it. So it means that ideally, we should actually know about all the limitations that this model has, and as a consequence, what would the limitation result in our model prediction, and incorporate that in our, the model monitoring section right here. Because we can't really, if we know nothing about the model, like say from a statistical perspective, then we always have to be reactive rather than be proactive. So I would say that there is, it's a hard question. So I would say that it really depends on, like when you have a data set, what informs you to choose that particular model. And now that you are aware of the model, do you know about the limitation? And if so, how can you address that proactively? So because there is no model that performs like 100% good and there's no cons, right? I mean, even for XGBoost model, it also has its own cons as well. So being aware of that is really critical. So it means that, not just blindly use a library, but also know how the library, is being implemented even, or, what are at the very least, what are pros and cons of the method you are choosing.
Yeah, you're absolutely right. I feel like there's so many moving parts when you're building a machine learning system. That's what makes it fascinating. Are there any more questions at this point for Chengyin? All right. If there aren't, I just have one ask for the audience is to please take a moment to answer the poll. Dave has set up a poll with respect to the session. It really helps us cater future talks that are interesting to the audience. So please do that. And I want to take a moment to thank Chengyin. Awesome talk. And like I said, a topic very close to my heart. So I'm very excited to present this. And great presentation. And thanks to the audience as well for being super interactive. That's what actually makes a session interesting. So thank you, everybody. I'll hope to see you in another session, and definitely stay on for a lot more sessions that are happening at MLOps. Thanks. And I'll see you probably in another session. Bye.
Yeah, thank you. See you again in the future conferences. Bye.